it was a tough year. I mean, with this Corona. I mean,
yeah, of course.
Like everywhere else. I mean, schools and especially preschools were out for big chunks of the year. So I mean,
I see.
and Amalia and Ruth were at home most of the time, or big chunk of the time. And
I see. And you have to take care of her. Yeah.
Yeah, I mean, I had to share it with Norma.
Well, my son went to work all the time except for the first 6 weeks, and his kid went to school. I mean, the preschool for most of the time, but
so
and they didn't get sick, neither of them, and they are not. I mean, and my son got vaccinated, so they are.
So I see Eyal smiling. I mean, he suffered from the same phenomena. It was really tough. Like you had weeks over weeks with your kids at home. It was.
Whenever I hear that the dad went to school, I went to work, I I start laughing. That's the way things should be.
Yeah. All right, I think it is time to start. So, and I already started the YouTube broadcast. So, Dani, are you ready? May I introduce you?
Yes, please.
Okay, so I'm very happy to introduce Dani Szpruch and his talk on the local coefficients matrix for covering groups and the restriction problem.
Thank you. Good afternoon or good morning, depends where you are. Thank you very much, Dima and Erez, for inviting me. So I would like to tell you mainly about an ongoing project, although we have accomplished something already with withFan Gao and Freydoon Shahidi. So this is the outline for today. First, we shall recall the definition of some arithmetic factors defined over periodic field F and discuss their relations. Some of them are really well known, some not so much, and the relations, I mean, some of them are actually new. Then we shall recall the definition of Shahidi local coefficients and plantar measures, and I'll focus on the simplest possible example, which is SL2. Then I shall start discussing our work, which is an analog of these coefficients for covering of SL2. Then I shall outline the picture in the GL2, in covering of GL2 case. This case, who are supposed to be related, are actually quite different, and we shall explain the difference between these two cases using restriction from between these two covering groups. One is the derived group of the other. And as we shall see, those relations we should start with would play some role there. Finally, if time permits, we shall see how this goes. I would like to discuss the restriction problem in greater generality. I mean, beyond principal series and parabolic induction, and in fact beyond the covering of GL2. So let me start with the standard notation. Let F be a finite extension of QP. We have the ring of integers O, and we have the maximal ideal inside O. We have Q as the cardinality of the residue field, and we have a uniformizer, a generator of the maximal idea, and we normalize the absolute value on F so that the absolute value of the uniformizer is 1 over Q. If the dx is a Haar measure on F, then we also have a multiplicative Haar measure in the usual way. We shall fix a non-trivial character psi of F, and then if A is an element of F, we have the character psi AX, which is another character. And of course, A maps to psi A is an isomorphism from F to its dual group. We look at the space of Schwartz functions on F, and we have the Fourier transform defined in the usual way. We always, of course, pick the self-dual Haar measure on F. I would like to go to the definition of Tate to remind you, the definition of Tate gamma factor. So F star is acting on SF by right translations. If chi is a character of F star, then we can discuss chi equivariant functions which translate with respect to chi when you hit them by right translation. And let's know by SF chi hat this space of equivariant functionals as is already implicit in Tate thesis and certainly known to Weil. The dimension of this space is 1. So let me construct a non-zero element in this space. You can start with a Schwartz function and then take this Mellin transform. It converges in some right half plane, so to a rational function in q to the minus s, so we have the zeta distribution. This zeta distribution has the reciprocal of L functions as common denominator. L functions defined in the usual way. This means that if we take away the denominator, then we have a non-zero element, chi s equivariant, non-zero chi s equivariant functional. And of course, chi s is just what you see here, chi twisted by absolute value raised to the power s. And then, I mean, it's an easy exercise to verify that if you swap s with 1 minus s, chi with chi inverse, and phi with its Fourier transform, then you get another non-zero element in the same one-dimensional space. So you must have a proportion factor, which must be a monomial function in q to the minus s. This is the epsilon factor. The epsilon factor is nothing but Gauss sum times q to the minus cs, c being some integer. And then if you group together all the poles and zeros here, then you get the Tate gamma factor. So it satisfies the following functional equation. And of course, you can plug a nice test function and get the Tate gamma factor as a value of a certain principal value integral. This actually looks like a Gauss sum, and this is how we should think of Tate gamma factor as a periodic analog to a finite Gauss sum, right? I mean, if it was a finite field, then there was no absolute value, and it was just summation over chi times psi. Okay, now here is the nth power Hilbert symbol that plays an important role in construction of covering groups. So we fix an integer which is at least 1, and we shall assume that f star contains the full group of nth root of 1. We denote this cyclic group by mu n, and then we identify it with the nth root of the complex nth root of 1, and forget about this identification. The nth power Hilbert symbol is a map from f star cross f star to mu n, and it's an antisymmetric bilinear form. Moreover, it's non-degenerate in the following sense. For any a in f star, you can define the following character, mu a. Mu a c is just the Hilbert symbol of a and c. And this one, I mean, sending a to this eta a character identified f star modulo the nth power with its dual. Of particular interest is the quadratic Hilbert symbol, which is actually an arithmetic object. It's defined, first of all, it's symmetric, just because -1 raised to the power -1 is still -1. And it's defined really nicely. I mean, it's the Hilbert symbol of 2 elements is 1 if A is a norm in the quadratic extension of F with square root of B, and otherwise it's -1. Here is the unnormalized Weil index. It is a fact that the function f psi defined this way is not an element in the Schwartz function. It's not compactly supported. However, if you take any element in any Schwartz function, then the pointwise product and the convolution of these two do lie in SF. And there is a theorem by Weil stating that there is a complex eighth root of 1 denoted by gamma psi, which makes, I mean, the convolution theorem be almost true for this function. Of course, this constant is independent of phi. And actually, when you plug a nice test function, you find out it's kind of look like quadratic Gauss sum of the second kind. Just want to note that sending A to gamma psi A is a well-defined function on f star modulo f star square, because you can always change the variables. Now, let's just for a moment assume that n equal 2, and let eta A be the quadratic character of f associated with A by the quadratic Hilbert symbol, as I just explained. So it turned out that we have the following expansion. Epsilon factors and Veil indices are really closely related. They are expansion of one of the others. This looks like something coming from harmonic analysis on the f star modulo f star square, and in fact, this is exactly what it is. And these are exact analog to the relation, the classical relation between the two quadratic Gauss sums on finite fields. The fact that we have here expansions rather than equality comes from the fact that there is more than one non-trivial element in the f star modulo f star square. But honestly, the way you prove these two identities is just mimicking the classical, the proof of the classical identity. And then for me, the most important property of the Veil index is the following. It behaves nicely with respect to the Hilbert symbol, quadratic Hilbert symbol. There should have been a 2 here. This means that if we divide both sides of this equation by gamma psi and call it the normalized Veil index, then we get a function which splits the quadratic Hilbert symbol. And again, there should have been here a 2. This is why, I mean, people who are doing representation theory of covering group love this creature so much, because, I mean, it helps you to parameterize representations. And then here is a nice theorem. This is a result of Khan. The normalized Veil index is actually an epsilon factor of a quadratic character, precisely this one. So I accidentally hit on this result when I toyed with the same technique I'm using for what to come, and I was quite surprised by it. But then I dug a bit. I asked my mathematical friends who asked their friends, and eventually someone came with this reference to Khan. Bruno Khan proved it in completely different way, and I have a new proof, which is just simple harmonic analysis on f star modulo f star square, of course, assuming this nice property, this nice splitting property. The last factor I want to introduce is relatively new. This is the metaplectic. I just want to say that this actually makes sense. I mean, Ichino used it on its work on Saito Kurakawa liftings, and Jay Sweeted used it, and Khan itself used it. And we have just used it on our work on covering groups. Here is the last arithmetic factor I want to introduce. This is relatively new. I defined it about a decade ago. You can modify the definition of the Fourier transform and define this twisted transform. So this looks like a Fourier transform, only you throw into the kernel this Veil index. Of course, what you get is not even defined on 0, and it's not an element of it's not a Schwarz function. Nevertheless, I mean, if you throw it into the integral defining the zeta distribution, then it's converged in some vertical strip. So we can discuss the zeta of this transform function. And moreover, we can get a functional equation mimicking Tate's functional equation with the new factor, which I call the metaplectic gamma tilde factor. As you shall see, it's played the same role when you do double cover of SL2 as Tate gamma factor played when you do the algebraic case. And when you plug a nice test function, you get gamma tilde. It's a value of really similar integral to the theta integral, only you have this Veil index here. So the gamma tilde factor is new, but this integral is not new. I think, to the best of my knowledge, a mathematician named J. Sweet working on the generate principal series of double cover of SP2N ran into it in the mid-90s, and he actually computed it. This is the next slide. But so let me just propose for a moment. Just by having this integral, here are some identities you can get. First of all, gamma tilde and gamma are equal on average. Namely, if you take your chi and twist it by quadratic characters and then sum over all quadratic twists, then you actually get the same. Moreover, you can get gamma tilde and gamma as a nice expansion of each other. Okay? And those are not hard identities at all. This is just simple harmonic analysis. So as I told you, J. Sweet ran into this integral in the mid-90s and computed it, and this is what he got. I did not. I mean, he never published this result. It is a preprint that some people are familiar with. I didn't know about this one, so when I needed to compute the integral, I brute forced it. And now, not long ago, I learned that one can prove this result in a new way, in really simple and natural way, using the same identities I've just shown you, plus something that to me look like a p-adic duplication formula. Okay, relating the value of gamma 2s chi squared to gamma s.
Excuse me. What was that measure d sub psi of z? Is it different from dz?
Where?
In your definition of the
Psi?
Yeah, d psi z, what is that measure?
I'm always taking the self-dual measure with respect to psi.
Okay.
Okay, I mean, this was already in the definition of Tate gamma factor. I should say that, I mean, this integral appears again and again. I mean, it appears in two recent work of Eyal Kaplan, one with Moshe Adrian and the other with Pram. It also appeared in the work of Nelson. And so I suspect that this one, I mean, you do see it as some kind of normalization factor is actually important. This result of Sweet is actually important. Okay, now I want to move to Whittaker functionals. As I told you, I'm going to give full details on SL2. I mean, just a reminder of the definition, but just before this, here is a quick overview. Suppose we're looking at quasi-split reductive group defined over F, and we take Levy M and its unipotent radical U, so we have a parabolic subgroup. And then we have a smooth irreducible representation of the Levy, and then as always, we consider a parabolic induction. Let W pi be the space of Whittaker functionals on the inducing representation, and let Wi pi be the space of Whittaker functionals on the parabolically induced representation. There is a theorem from Rodier from early 70s stating that these two are isomorphic. These two vector spaces are isomorphic. Moreover, there is an explicit isomorphism between these two, given by what people call a Jacquet type integral. Now, if we take a standard intertwining operator, then by duality, we have a map from the Whittaker spaces, of course, on the other direction. And then the point is that since this integral of Jacquet type do identify these two spaces as the space of Whittaker functional on the inducing representation, then one may consider a matrix representing this map, right? I mean, you don't have a canonical matrix or unique up to conjugacy matrix representing a map between two different vector spaces unless someone before them identifies them. And this is precisely what the Jacquet type integrals does. Of course, as we all know, all these Whittaker spaces are either trivial or one-dimensional. This is the famous uniqueness of Whittaker model proven by Shalaika and then Gelfand-Kashdan and then Berenstein-Zelevinsky. So it's easy to forget that those Jacquet type integrals actually identify one-dimensional spaces. In the generic case, when we actually have Whittaker function, Nonzero Whittaker functionals, this one-by-one matrix representing this map after identifying these spaces is precisely Shahidi local coefficients, or rather the reciprocal of Shahidi local coefficient. And this actually makes a lot of sense to us because we're looking to define a matrix representing this map in the context where there is no uniqueness of Whittaker model. So in order to make sense of it, I mean, in order to start extracting invariants from the characteristic polynomial, we somehow have to choose bases on both sides in some coordinated way, in some compatible way. And this is exactly what those Jacquet type integrals do. So let me give you full details on SL2 in the SL2 case, which is of course very well known. SL2 is the group of 2x2 matrices with determinant 1. We have the standard unipotent radical of upper triangular matrices with 1 along the main diagonal, which is isomorphic to the field. And we have the diagonal subgroup, which is isomorphic to the invertible elements in it. And then we have the Borel subgroup, which is the semi-direct product of U and H. And we have the non-trivial Weil element. This Weil element normalizes the torus, except if, in fact, it is the only non-trivial element in the normalizer modulo the torus. And those three generate SL2. We take a representation of H and extend it trivially on U, and we get a representation of B. This is how you do parabolic induction, right? And in fact, when you talk about SL2, but not only its covers, HF is commutative, so all you induce from is a character, one-dimensional representation, so you get a principal series representation. Then you have the intertwining operators. To define them, of course, you reintroduce the complex parameter S, and then you define these integrals, which whatever converges, I mean, it's easy to check that they're intertwining I chi with I chi inverse minus S. And in fact, they do converge in some right half planes, and they have a meromorphic continuation as the rational function in Q to the minus S. For a Zariski open set, those are analytic functions, and I chi is irreducible. So in particular, the dimension of its home space is 1. This means that if you take the intertwining operator back and forth, you'll get a scalar map. This scalar is what people call a Plantar measure associated with chi. This is an invariant of the inducing data of chi. And it has few applications. Here is one I want to consider today. The Napstein theorem, dimension theorem, tells you that this dimension is 2 if and only if we have a symmetry here, and the Plantar measure is analytic. Of course, chi conjugated by W, just chi inverse. What this non-trivial Weil element does is replacing, swapping the two coordinates on the diagonal. In this case, the intertwining operator is not a scalar map. So here you go. Here you get the scalar map and a non-scalar map, the two elements spanning this home space. In particular, this means that if you're inducing from a unitary data so that your induced representation is unitary, then it's reducible if and only if chi is stabilized by the Weil element, and the Plantar measure is analytic. One way to compute this Plantarel measure is through multiplying two Shahidi local coefficients. And precisely, if you take a smooth representation of SL2, this is the actual definition of Whittaker functionals for SL2. Those are functions which translate according to psi when you hit your vector with sigma. And let's denote by W sigma psi the space of Whittaker functionals. I would like to construct now Whittaker functionals on this representation. So on some right half plane, these integral converge, and then of course it's easy to verify that they do exactly what they are supposed to do. These are what I call the Jacquet type integrals. Here, I mean, the space of Whittaker functional on the induced representation is just a space of functionals because there is no unipotent radical when you do this when you take your Levy subgroup to be just a torus. The analytic continuation of this integral is a Whittaker functional. Now, what is the dual map I mentioned earlier? If you have a map between two representations, then you have a map between the Whittaker spaces just by composing. In particular, this implies that since the composing the intertwining operator back and forth give you the Plantarel measure times the identity, then I mean, you'll get the same function when you compose those dual maps, those Whittaker maps. Hopefully, this is easier to analyze. And of course, the reason it's much easier that those are operators acting on one-dimensional spaces. By the uniqueness of Whittaker model, right? I mean, those one-by-one representing matrices, you have Shahidi local coefficient, or rather what we have here, the reciprocal of that one. Just want to mention, although it's purely a local talk, that these two functionals arise naturally when you take local, when you do Euler expansion of some Fourier coefficients of Eisenstein series. And the reason those Fourier coefficients are Eulerian from the first place is due to the uniqueness of Whittaker model. This is gone once you move to the covering groups. And as I mentioned earlier, and this is the key point for our generalization, those two identified the two Whittaker spaces with the space of functionals on the inducing representation. Of course, you can compute the local coefficient by taking a nice test function. And what you hit on is this integral. This is the same integral giving rise to Tate gamma factors. So this is how we know that Shahidi local coefficients are Tate gamma factors. And of course, since, as explained earlier, the product of two local coefficients is a Plantarel measure, we have computed the Plantarel measure. And of course, we have the reducibility result because it's so explicit. Given that chi is unitary, then the corresponding principal series is reducible if and only if chi is non-trivial quadratic character. If it's trivial, then you will have a pole here coming from the L functions. Finally, I'm now moving to the metaplectic groups. So we are considering n-fold certain topological central extension of SL2 by mu n. This means that we have the following short exact sequence. This is not a linear group, and namely you cannot embed it. It's not a linear algebraic group. You cannot embed it inside the GLK. I'm not going to do any fancy computations here, but just to give you the flavor of how this is defined, I mean, you can realize this group as a set SL2 plus times mu n, and then you have the multiplication. You multiply two matrices, you multiply the mu n elements, and then you have the cocycle, of course. And the cocycle is somehow made of a Hilbert symbol. This is a construction due to Kubota from the late 60s. So you have here the n power Hilbert symbol, and you have here this x function which asks you, are you in the open or closed Broussard cell? we have the preferred section SG equal G times 1. This is, of course, not a group homomorphism. And for any subset of A of SL2, we denote by A tilde its pre-image in the cover. A representation sigma of the covering group is called genuine if the central elements mu n acts according to the identification we had with the complex nth root of 1. And of course, we only care about genuine representation. We don't want any representation coming from lower degree cover or from the linear group. It is a fact, and this is very general, not for SL2, that the covering group split canonically over the unipotent radical. So we again can discuss the representation of the inverse image of the Borel subgroup in a similar way we do in the linear case, and we can consider principal series representations. Only that now, of course, sigma is a genuine irreducible representation of H tilde, not necessarily a character. Okay, I mean, here is the cocycle between two inverse image of the two metaplectic torus elements. This means that if n is greater than 2, then this is not symmetric, right? So once you move beyond the double cover, these are not going to be commutative anymore. So we are not talking about one-dimensional representation, but this is not too bad because the metaplectic torus is a Heisenberg group. And by this, I mean a two-step nilpotent group whose center has a finite index. So giving a genuine irreducible representation of this metaplectic torus, its isomorphism class is determined by the central character. In particular, the dimension is finite. The dimension is the square root of the index of the center inside the torus, metaplectic torus. For n equal or greater than 2, and of course 1 also, one can identify these central characters with d power characters of d power of characters of f star. D is either n or n over 2, depending whether n is even or odd. This identification is usually canonical, but by usually I mean unless n equal 2 mod 4. So the first non-canonical case is n equal 2. In these cases, the parametrization involves the Veil index. This is why we care about it so much. So from this point, all the chi you will see are characters of F star such that chi d is associated with the genuine irreducible representation sigma of H tilde. In cases where this parameterization is not canonical, we don't have to worry because what will come into discussion eventually is the square of this one, which is canonical. Okay, is chi to the power n. Chi to the power n is always canonical. So uniqueness of Whittaker model fails. Here the theorem Fan, Gao, Shahidi, and myself proved a few years ago. Uniqueness of Whittaker functionals holds if and only if H tilde is commutative. And this is true not for any Berlinski-Deligne covering group of a split reductive algebraic group. I mean, it's, say, 15 years ago, I proved the uniqueness of Whittaker models for the double cover of SP, where the torus is commutative, the metaplectic torus is commutative. And when you go through the details, you find out that you are actually using the same machinery as in the algebraic case. And at one point, it's crucial that the metaplectic torus is commutative. And then it's really easy to show that if your metaplectic torus is not commutative, then uniqueness failed. This failed already in the level of principal series representations. And then our relatively recent observation is that whenever the torus is commutative, you can, the metaplectic torus is commutative, you can repeat this argument. This means that when n is greater than, it should have been here 2, when n is greater than 2, not 3. When n is at least 3. When you move beyond the double cover, you don't have uniqueness of Whittaker model anymore. But the space of genuine functional or genuine principal series representation is still finite. Just for a moment, let's stick with the abelian case, with n equal 2 case, the last abelian case. In this case, you do have uniqueness of Whittaker model, and you do have a Langlands-Shahidi theory. This was a big chunk of my PhD dissertation, or all of my PhD dissertation. You can compute the metaplectic local coefficient, produced in the same way, and you hit off on this integral when you compute the local coefficient, which tells you that the local coefficient is the metaplectic tilde gamma factor, and this is why I introduced it initially. So the metaplectic gamma factor plays the same role as for the double cover as tilde gamma factor is playing for SL2. Suppose now that n is equal or greater. There is a second typo here. At least 3. So we have used the same Jacquet integrals I've mentioned earlier and pointed out in the SL2 case to identify the two Whittaker spaces with the space of Whittaker functionals or just functionals on the inducing representation. And we have a matrix now representing this map between this dual map between the Whittaker spaces. This is just a tiny technical result and remark. If n is this is third typo. If n equals 0 mod 4, not none. If n is equal 0 mod 4, it should have been equal. We have to assume that some tameness assumption. Otherwise, I mean, we are good to go. In the odd cases, in 2 mod 4 cases, we don't need this assumption. And we have shown that the entries of this matrix, once you compute them, is always a linear combination or of gamma or of tilde gamma factor or metaplectic tilde gamma factor. So the metaplectic tilde gamma factor is showing its face again. And moreover, if you pick natural bases, then you get natural linear combinations. The coefficients are just going to be Hilbert symbols. So our work gives a new interpretation of the scattering matrix introduced in the 80s by Kasdan and Peterson, their seminal paper on metaplectic forms. So in that paper, they considered a metric represented this map for covering of GLN when the inducing representation is unramified. Of course, everything is tamed and unramified. And initially, Kasdan and Peterson were interested in computing the rank of this matrix, because this tells you a lot about the dimension of Whittaker space on the theta representations. But they did not care about this matrix being in, or its characteristic polynomial being invariant of the representation. Namely, they did not care about choosing the bases in a compatible way. So it's not the scattering matrix, while very important. I mean, it was then computed in far greater generality by McNamara and utilized by many people, say by Gao when he computed the dimension of theta representations, of Whittaker space on theta representations. Nevertheless, the scattering matrix is not a valid source for arithmetic invariance simply because its conjugacy class is not an invariant of your inducing representation. So many people are now using the scattering matrix. For example, it's related to the so-called R matrix in the work of Brubaker, Busiumet, and Bump, where these people are actually correcting the scattering matrix in a fashion which is really close to what we did. So it seems that, I mean, we suspect that we are looking at the right object. Evidence would come just now. First, I mean, we can compute plantar measure because we can compute matrices, multiply matrices. And here is what you get. I mean, this is a nice generalization of the formula we had for the n equal 1 case. I mean, if you replace n by 1, then this is exactly what we had for SL2. And then, of course, you can do reducibility result. I mean, the Knapp-Stein theorem we've used was extended by Savin to parabolic induction on covering groups, provided that inducing subgroup is maximal. And very recently, Kai-Walu generalized Knapp-Stein dimension to any parabolic induction on covering groups. It follows that if n is even and sigma is unitary, then the principal series is irreducible. If n is odd, then reducibility results, which are known to us, known already, resembles the linear case. This distinction between even and odd fault covers of SL2 is actually agrees with the Weissman theory of dual group and L groups. This theory states that the dual group of n-fold cover of SL2 is either PGL2 or SL2, depending whether n is odd or even. I mean, we're quite surprised to find out that this theory does not explain a trichotomy we shall now describe. I mean, when we started computing the trace and determinant of this matrix, which are invariants, we found that there are actually three families here: the odd fault covers, the two mod 4 fault covers, and the zero mod 4 fault covers. Those are three different creatures. So suppose you want to compute the trace. This is what you hit off. You hit off an integral which kind of look like what you had when you do the one-dimensional case, the n equal 1 case, only you're integrating over the data, which is the central character. This kind of look uniform to all covering groups, but this is what you'll get. You get the sum of gamma factors unless n equal 2 mod 4. And when n does equal 2 mod 4, you hit on metaplectic gamma factors. So it seems that the odd fault covers and the 0 mod 4 fault covers goes together. And the 2 mod fault covers are a separate entity. But this is not quite, because actually, when you're doing 0 mod fault for covers, you can actually get some of gamma tilde factors. And it's not clear for us what is the natural way to do it. Both of them are correct. I mean, we had these relations between the gamma factors. In the unramified case, we can actually compute those sums. And we find out that the 0 mod 4 cases behave differently than the other cases. I mean, and then we compute the determinant in the unramified case. First of all, a priori, the product of two determinants must be some power of the Plantar measure, just because those are, you take a product of two determinants, and so you get the dimension times the scalar, right? And when you compute them in the unramified case, you see that you get completely 4 different results. So those are actually 3 different families. And so these are the evidence for what we call the SL2 tilde trichotomy. Here is a new invariant, which was at least initially the goal of this game. If n is not equal to 0 mod 4, then the dimension of the inducing representation is odd. So it makes sense to normalize your determinant by this even power of the Plantar measure. And of course, given this relation, which is of course if we get for free, this means that this new invariant behave like Shahidi local coefficients. Namely, if you multiply those two, you get an actual Plantar measure. This you cannot do when n equals 0 mod 4, because then you actually don't have here an integer. And when you compute it in the unramified case, in fact, this is just a reinterpretation of the slide we just had. You see that you actually get a gamma factor or a metaplectic gamma factor. So this construction is an example of an inductive process to define gamma factor, starting with the determinant and Plantar measure, which are object of less subtlety. I now want to tell you what we find out in the GL2 case, covering of GL2 case. So first, for a fixed n, we have bunch of covering of GL2 constructed by Kubota. We have the C-twisted one. And if you want to think about cocycle, then here is the cocycle. This is the same cocycle we had before, only we throw here the determinant, which of course is gone when you go back to SL2. And then you twist it by some C power of the N power Hilbert of the determinants. While for fixed n, different twists of covers of GL2 are not isomorphic, they all have the same derived group, which is SL2 bar. Remarkably, when we computed the invariance, we found out that the trichotomy we encountered is gone, or completely gone, or almost completely gone once we move to covering of GL2. And this is in fact a bit surprising because all the local invariants coming from Shahidi local coefficients, local matrices are determined by unipotent elements, which all lie in the derived group. So it's kind of surprising that we have this trichotomy on the level of the derived group, but not on GL2 bar, GL2 tilde. So let's call H prime the metaplectic torus inside the GL2. Let's pick an irreducible representation of this torus, metaplectic torus. And let's consider the corresponding principal series representation. Let's pick one genuine representation of the metaplectic torus on the derived group, which lies inside the inducing representation. This is just a finite dimensional representation. So when the restriction will be just a finite sum. So take just one summand. Maybe you have more than one isotypic component. Take just one. And let chi be a character of F star such that chi is associated with sigma. Sigma being just one random SL2 tilde irreducible representation inside the pi. Let mu(n) be the Plantarel measure for the GL2 tilde principal series representation. A priori, it must be equal to the Plantarel measure of sigma, just because we compute it through the local coefficient matrix, and the local coefficient matrix is determined on the level of the derived group. Of course, what I should have mentioned is that the restriction commutes with all the relevant intertwining operators. So we have a formula for Plantarel measure, and we have irreducibility result. You don't have reducibilities on the unitary axis. If you compute the trace of the local coefficient matrix called GL2 bar, then you actually hit on some formula which does not differentiate between different n, except maybe for this number, which has to do mainly with, if you fix n mainly with your twist. And if you do the computation in the unramified case, then again, you don't see any significant difference between different n. When you compute the determinant in the unramified case, you again don't see, you again take product, you again get product of Plantarel measure and gamma factors. You never see gamma tilde factors, and you don't see any significant difference as you vary n, maybe except for this pathetic sign, which is 1, unless -1 is not a square and n is equal to 2.4. And I should say that we have general formula for much larger family of covering groups in the unramified case for essentially all Belinsky-Deligne covering groups. And you always see product of Plantarel measure and gamma factors or gamma tilde, never both. Some of them you don't see any, like in the SL2 case example I've shown you, SL2 tilde example I've shown you. But this is a very general thing. I do want to explain this gap between the formulas for SL2 bar and G tilde, SL2 tilde and GL2 tilde. In the odd case, the explanation is easier. In this case, the center, when you take the center of the metaplectic torus on the GL2 level and intersect it with the derived group, you get the center of the metaplectic torus on the derived group. But this just means, since the central character determines the isomorphism class of a general representation, this means that the restriction of pi to SL2 tilde contains just one isotypic, should have been isotypic component. So sigma was not random in the odd case. There was only one sigma. And in fact, what you get when you restrict your principal series representation to the derived group is a direct sum. Is one isotypic component. I mean, I wouldn't call it an isotypic component just because no one tells you that those are a priori irreducible, but you get the direct sum of fully induced representations. Note that generically this factor is not one. Namely, failure of multiplicity one occurs everywhere when you do restriction on covering groups. This is very rare on linear algebraic groups, and in fact it happens almost all the time when you do covering groups. I mean, it wouldn't happen when you do two modes, when you do the double cover, but otherwise it's happened almost all the time. And of course, once you see this, then you understand exactly how to gather the invariants for GL2 tilde. I mean, because your local coefficient matrix is just a block diagonal matrix, and you just have the same block repeated over and over. The even case is much more interesting. First of all, in this case, when you take the intersection of the metaplectic torus inside with the derived group, you get actually a group which is actually smaller than the center of the metaplectic torus inside the derived group. And this would, what it means is that when you take a principal series representation of GL2 tilde and restrict it, you will get a sum of 4 isotypic components. Okay, so here we view this eta as a quadratic characters due to this identification. Okay, and again, multiplicity one phase. Moreover, if you start with an unramified representation, then this restriction I've just discussed contain 2 unramified isotypic components and 2 ramified ones. So when you want to do the calculations of for GL2 tilde I just described, you need to take into account some ramified calculation SL2, which is, this was quite a surprise for us, that you have fully induced ramified representations of SL2 tilde sitting inside unramified representation of GL2 tilde. I should say that the n equal 2 case, I mean, when you do n equal 2 case double cover, this was known to Piasecki, Shapiro, and Hilbert in the early 80s. And then the other thing that came in, so you have, so the local coefficient matrix would be a block matrix, but those will be actually different blocks. So when you want to take all these blocks into account, then you actually have to consider all those invariants I initially introduced and all those identities I introduced. So all these subtle relations. So this is as far as principal series goes, and now it's a good place to stop unless we have some more time and I can tell you about restriction problem in greater generality. I mean, Dima, what do you say? Should we stop here? Should I continue for 15 more minutes or so? I mean, I'm good either way.
Yeah, let us just ask if there are any questions up to now, and then continue.
I wanted to verify in the unramified case, your identities are not just for SL2 or GL2, right? Your computations are for arbitrary Brylinski Deligne covariance, right?
The determinant is yes. In the unramified case, we have computation much greater generality. Yes. This is not to say that I
But also.
Come again, Eyal?
Yeah, I wanted to verify. You mentioned that these strange phenomena disappear when you look at coverings of GL, but is this still true when you look at arbitrary Brylinski-Deligne coverings of GL, or just when you look at those you described, the Cash and Patterson with the parameter C?
I'm not sure yet. I mean,
because they share the same L group, and I'm asking because they share the same L group, and others have different L groups. Sometimes it's GLN, not GLN times GL1.
Yeah, I'm not sure I can give you a result, an answer on the top of my head just now. I mean, that I can describe very easily the relations between covering group and its derived group. So I really, honestly, don't know. I mean, probably, right, we're talking about rank 1 intertwining operator. So probably what I told you is correct when you do covers of SP2N and GSP2N. And other than this, I mean, I'm not certain.
So there was also a question in the chat about NC.
What was NC?
Yes.
NC was just an innocent integer. I mean, at one point, I think it was in one of the slides. This is NC. This is a miserable integer that has to do with N and C. But unless something dramatic happens, this is actually an integer which is greater than 1. And it does appear as something controlling the multiplicity.
Okay. So I think you can continue.
So what's a restriction in greater generality? Let's take the Kazan-Patterson cover of GL2N. And in fact, I'm thinking about the cocycle. I like to work with the cocycle constructed by Banks, Levy, and Stepansky just because it is block compatible. And by restriction, we can get covers of GSP2N and SP2N. And of course, the basic case is when n equal 2 and m equal 1, double cover of GL2 and SL2. This case was known already to Piasecki, Shapiro, and Hilbert. G tilde is the derived, G naught tilde is the derived group of G tilde. Now take S to be the group of scalar matrices inside G. So to speak, the center of G, no more, no less. It turned out that the inverse image of the scalar matrices is the centralizer of the G naught tilde inside G tilde. S tilde is abelian if and only if n divides 2m times 2m minus 1. Namely, we have like a really tight relation between the rank of the algebraic group and the degree of the cover. So we should think about it that typically S tilde is not abelian. In the cases where it's not abelian, it's a Heisenberg group, which is not too bad, but yet we have a non-abelian centralizer of the derived group inside the covering group. And this fact only give you some nice phenomena. Take a smooth representation of G tilde, genuine representation, irreducible representation. S tilde is acting on the space of Whittaker functionals on this representation, right? Just because it's commuting with the derived group, and the unipotent elements are elements of the derived group. So this means that S tilde is acting on the space of Whittaker functionals. And this is a genuine representation space of S tilde. This means that, of course, if this space is not trivial, then it's not one-dimensional. It's actually greater than the index of S tilde and its center. This means that in these cases, uniqueness of Whittaker model fails for any pi. So this is complete contrast to uniqueness of Whittaker model for algebraic groups. It never holds. And for this reason, when you restrict, this is more or less for this reason, just for having a non-abelian centralizer, when you restrict pi to the derived group, you never get a multiplicity-free restriction. So failure of of multiplicity one, or both multiplicity one, is very common on covering groups. Now, it turned out that certain even-fold covers are very interesting and behave different than others. So let's write n as 2 to the power L times an odd number, and let's write m as 2 to the power t times some odd number. So L and T are the twoadic valuation of n and m. If L is less than T, namely if the degree of the cover is less even than the rank of the underlying algebraic group, then the center of the metaplectic inverse image of the center is the same as the center of the group. The more interesting case is when L is greater than T. So the basic example would be take a twofold cover of take a twofold, take a double cover of GL2. This already happens there. It turned out that in this case, ZS tilde is larger than the center of the covering groups, and the group is actually F star modulo. I mean, the ratio group is just the quotient group is just F star modulo F star square. Take this G plus group, which is just a scalar matrices times the derived group, and now take its inverse image. As in the algebraic case, it's a normal subgroup inside the cover. And the index is always, the quotient group is always F star modulo F star squared. And then G tilde modulo G tilde plus acts on the isomorphism of irreducible representation of G plus by conjugation. And the point is that if L is greater than T, this action is free, simply because the action does not preserve central characters. This is just by examining the relations between the center of the inverse image of the scalar groups, scalar elements, and the center of the group. On the other hand, the representation theory of this weird group is quite easy. I mean, take a genuine representation of the derived group, take a genuine representation of the torus, of the metaplectic centralizer. Both of them, of course, assume to be irreducible. Assume some compatibility, namely that they coincide on this finite intersection. And then you will get a general representation of this G tilde plus. And here's the theorem we recently proved. Any representation, if you start with any representation of the derived group and of the inverse image of the scalar matrices and induce it, you get an irreducible representation. And any representation, it can be proved that any representation of G tilde is obtained this way. This means that more or less G tilde is a dummy group, right? Because all its representation theory is coming from the derived group. This phenomenon on GL2 was, as I mentioned, was known for PS and Hilbert, and for certain untwisted cover, n-fold cover of GLN was known also to Adams. The dual of this theorem would be to describe the restriction. So if you start with the general representation of G tilde, take any irreducible component G naught tilde irreducible representation lying inside your representation. And then it turned out that you have the following restriction. So you'll have this pi naught appearing as one isotp component, and then you'll have a bunch of others. All of them are twisted by the action of G tilde modulo G tilde plus. Of course, this is by complete contrast to the intuition we have from the algebraic group. And the multiplicity is independent of pi and is usually greater than 1. So failure so the restriction is never multiplicity free, which is kind of weird. Those are
Do you know what C is?
Yes. It's completely explicit. It's becoming too technical at this point. We know exactly what C is. It's some number you cook from N, M, and the twisting C. I mean, we know what it is. I mean, we have it in the preprint we uploaded to the archive on February. And last, in this case, where L is greater than T, we have the same theorems for any parabolic subgroup inside G, or rather any inverse image of a parabolic of a Levi subgroup inside G tilde. And the theorem behaves nice with respect to parabolic induction. If n is even, then one can relax the condition L greater than T, so and n is even, so that it holds for some M tildes, but not for G tildes. And in this case, when you do this relaxation, namely when you modify your covering group, then you get a nice criteria for parabolic induction, for irreducibility of parabolic induction. The simplest example with which I want to finish is when you go to the Borel subgroup, when M is T, when M is just torus. So its inverse image is just a Heisenberg group. Here is the simplest case, n equal 2 and m is even. Say we are doing a two-fold cover of GSP4. In this case, all the metaplectic toruses are abelian, although it's not necessary for the general theory. Let's denote by T naught the metaplectic torus inside G naught tilde, and let's U be the unipotent radical as always. So it turned out that any principal series representation of G tilde can be realized by inducing from this inverse image of the scalar matrices times the torus in the derived group. And of course, these two, psi is the representation of the inverse image of the center, and chi is the character of the metaplectic torus inside the derived group. Suppose you just consider with the compatibility, of course, with the compatibility requirement. Suppose we just consider the induced representation on the derived group by inducing from chi. Then if chi is reducible, then pi is reducible. This is a simple induction by stages. But what's more interesting is what happens when this is irreducible, which happens all the time, right? Most of the time. Then it turned out that pi is reducible if and only if the following condition is satisfied. We have the action of the veil group on the inducing data, and we also have the action of the metaplectic torus on the covering groups out, which, I mean, we care about elements which lies outside the metaplectic torus inside the derived group. In the cases where these two give you equal isomorphic representations, equality in the case of characters, namely in the case where the action of the veil group, of the Weil group, agree with the Weil element, not group, agree with the elements of with the action of torus element, then you get reducibility. And the point is that, especially in the case of principal series representation, it's not hard to construct these examples. And among these examples, you always find unitary unramified principal series representations. And at this point, the existence of these representations is kind of a mystery, because, I mean, we are accustomed to having reducibilities on the unitary axis coming from some analytical function having a pole or something of this nature. But this is a reducibility of completely different nature. It has to do with with the way that the rad group is sitting inside the covering group. Although the result, as they explained here, does not mention the covering group or mention it very loosely. And there is no analytical function having a pole here. So this is like a reducibility of unitary unramified representation, which is of completely new type. So I think I'll stop here and thank you for your attention. I hope it wasn't too long or technical.
Thank you very much. Questions, please.
Yes. So can you just go back one slide?
Yes.
Okay, so first, just here, G, I kind of lost it. At some point, G was supposed to be GL, but...
No. G was never GL. I'm just saying I was interested in covering of GSP2N and SP2N, which are obtained by restricting covering of the covering of GL2M. Okay, in my example.
Okay. So if this reducibility is not related to some analytic, although maybe you will find some analytic criteria, but at this point no. So how do you prove such a result?
Of course, I mean you can do reverse engineering and show that there is analytic function after all. I mean you can do Napstein theorem and you can show that some analytic function having a pole. But the point is that you can prove it without knowing anything about plantar measures. And this is nothing but a mathematical theory, but nothing but inducing from a normal subgroup of finite index. The point is that you have this remarkable action of G tilde modulo G tilde plus on the inverse image of the scalar matrices, which is, has no analog in the linear algebraic case. This is why it's so interesting.
In your last theorem, when pi naught is irreducible but pi is irreducible, can you describe the constituents explicitly or something, or it's an abstract theorem?
Probably in the unitary case, in the unitary unramified case, you can do it.
You can do that.
Yeah, probably. I think I'm in the unitary case. I more or less did it for a double cover of GSP2N, and this is probably. I can't say I thought it thoroughly, but this is not an abstract theorem. This is like a finite group theoretic theorem, which is typically very explicit.
Well, at least for SL2, for GL2 and SL2, I do remember that you described explicitly the constituents.
No, but it does not happen for double cover of GL2 and SL2. Remember that you have to have a double cover and you have this relation between L and T. So you have to go to a bigger group to see this phenomenon. The simplest example would be twofold cover of GSP4. It does not happen. It's not something that you see on the level of GL2, SL2, never.
Is there some way of organizing these reducibilities and so on and so forth in terms of some sort of Langlands parameters for these the L groups of these coverings? In other words, here you're finding the phenomena in terms of these characters and restrictions and their properties. But it's sort of, maybe if you organized it in terms of some L group parameters, they would also give you another description of them and might put them in a better landscape. Is that possible?
this is correct, and we actually said stuff about this. And I think Gao, I think, is in the audience, and I think he can give you a more detailed answer than I can. But these cases where you have those funny reducibilities, so
Right.
when we say unramified, what do we mean? We mean you take your standard hyperspecial maximal compact subgroup and you embed it inside the cover. But the point is that in these cases,
using your standard section. Using your standard section.
I mean, using what you have, right? I mean, embedding.
Yeah, okay. Yeah.
It's not usually the standard section, but moreover.
No, but right, there's a standard way. Yeah. Okay.
So in the derived group, there is a standard and unique way, but not on the level of G tilde. Moreover, on the groups that you do have those funny reducibilities, it turned out that you have more than one embedding. You have two non-conjugated embeddings. So the whole so this is somehow give you some non-canonical parameterization of the L parameters of the data, and it has a lot to do with that.
I see. Okay, good. Thank you.
I think we have some results with respect to the S group, and in the second paper, I think Fan, we have some in terms of the S group and R group and those stuff and Langlands parameters we have.
Yeah, and I think it has to do with what I've just mentioned. So the answer is correct.
Okay, any further questions? If not, let us thank the speaker again. And, our speaker for next week is Marie-France Vignera. She didn't send me a title yet, but when she does, I will update. So, see you in a week.
Nice evening. Rather nice day.
Yeah. Thanks, Doc. Nice talk.